Okay, so last time, okay, let me just start with what we're doing. So this is a theorem. Okay, so the plan is I'm going to do, I'm going to talk about something today, about something how to compare cardinalities. And then the next time, I owe you some things about finite sets. In particular, I never showed you, so we defined Dedekinds' definition of infinite, right? And then, but I never showed you that an infinite set and a not finite set are the same thing. So I have to do this, and we'll try and talk about the pigeonhole principle. Let me recall what we were doing last time, and I want to talk about this and how this comes into play, this particular theorem. So last time, the goal was to show that the power set of the natural numbers, so it was isomorphic to the, or was the cardinality of the natural numbers was equal to the cardinality of the power set of the natural numbers is equal to the cardinality of the continuum, the cardinality of the real numbers. Okay? So the strategy was the following. So we showed that the power set of the natural numbers, so this was, or let me just write down bijection. Well, let's do this. The power set of the natural numbers, and we established an explicit bijection between power sets and functions from the set to 0, 1, right? Like this. Okay? So this is a set of functions, right? And then we have that this was in bijection with this interval 0 to 1. This is something that I said. And then we used that trick where I had that like semicircle argument, and that was the same cardinality here as the real numbers. So this line here was like the semicircle trick. Okay, this was a general theorem. So these two things were, this is a general fact. And it said that characteristic functions, so subsets, correspond to characteristic functions. That's how we got this one. Okay? And then from here to here, there was a little bit of a cheat. And I said that there was an exercise at the end. Okay? So from here to here, the idea was that we took a sequence, B2. So we said that functions on the natural numbers are the same thing as sequences, right? And we mapped this to a number, right? Well, let me show you. It's not an element of this, but if we got rid of the absolute values, it would be an element of this thing, right? So maybe I can write it like this. Here to 0, 1. Okay, and we mapped it to a number, right? And here's the interval 0, 1. And the number was the sum of bi 2 to the minus I, here from I is equal to 1 up to infinity. Okay? And so the issue was, okay, so we have a function from here to here, and there's this guy here. So the issue is the difference between the closed interval and the open interval. Okay? So we had this thing which took the sequences of 0, 1s and it mapped it to this number, and you know, that's that it represents in binary. Okay? So the main difference, the gap for showing this theorem was to show, so we have a gap, was showing this interval, and the open interval and the closed interval are in bijection. Showing there is a bijection between the open and closed interval. Okay, so okay, does that make sense? Do you guys remember this? Okay. Okay, so what I labeled this as an exercise last time, and I want to kind of, I'm going to show you this, that there exists a bijection in two ways. One, I'm going to reference this theorem, and the other one I'm going to do directly. Okay, and the idea that I use here, the idea that I use in this direct proof, right, which is given as an exercise sometimes in other classes, will, and I think it's a little hard for an exercise, but the idea that I use in that exercise is kind of there's a more general idea to this. Okay? So let me start by doing the kind of direct approach first. Okay? So let's do this. There's a bijection between the open and closed interval. All right. So a lot of people we're used to thinking about like continuous maps, and so this direct thing you kind of have to break continuity a little bit. All right. So let me do the claim. So lemma. All right, so the lemma is that, that these two things are, there's a bijection between the closed interval and the open interval. Okay, so here's the proof. Okay, or solution of the exercise that we stated at the end. Okay, so what we're going to do is we're going to let f be a map from the closed interval to the open interval, and we're going to define it in the following way. Okay, so I'm going to write down the function first. This function will look weird, okay, but it comes from a picture, and I'll show you the picture. So the function that I write down came from a picture. All right, so it's going to be a half if x is equal to 0. And it's going to be 1 over 2 to the n plus 2 if x is equal to 1 over 2 to the n, okay, for some n that's a non-negative integer. Okay, so this could be 0 here. Okay, and then it's going to be the identity, x is just going to be the identity otherwise. All right, so I claim that this function is a bijection. So we claim okay. Okay, so let me show you the idea here. So the idea is to build, okay, so let me tell you, maybe I'll tell you a story first, okay? So, so there's this thing called the Hilbert Hotel, okay? So there's a countably infinite hotel, all right? It's called, I don't know, Hilbert had a hotel, right, in mind. And it's just one really long hallway with a bunch of rooms. All right, and suppose the hotel is full. Okay, so there's all the rooms in this countable hotel are full, and so what you can do you can always accommodate more guests. Okay, and so here's how you accommodate more guests. Okay, you tell everybody in the rooms, right, to go outside the room and then go to one room down. Okay, and this leaves the first room in the hallway open. Okay, do you guys get what's going on? And then you can always take a new guest this way. Okay? And so what we're going to do is these powers of 2 are going to be like our hotel. And the new guests are 0 and 1, right? So these are the new guys that aren't in this this interval. They're not in the open interval 0 to 1. Do you guys see that? So we're going to make room for these two guests. Okay? And so let me draw the picture. Okay, so here's this interval. Here's a 1, and here's 0. All right, here's a half. So 1 is, this is 2 to the minus 0, by the way. Okay, this is a half. This is a fourth. This is an eighth, right? And this is a 16th, and so on and so forth, okay? So you can keep going, etc. Okay? So, so in the map that we described, 0 here, so it goes to 1/2, okay? 1 goes to 1/4. So this is 2 to the 0. 1 over 2 to the 0 goes to 1 over 2 squared. 1 over 2 squared is 1/4. Okay? 1/4 goes to 1/16. 1/2 goes to 1/8, right? And then it continues in this way, right? So it'll go 2 doors down, right? So what we've done is we've kind of taken all these powers of 2, right? These reciprocal powers of 2, and we've shifted them down, right? So we've cleared up space by shifting all the powers of 2. And then things that aren't on the, we have points that aren't powers of 2, we'll just keep the same. Does that make sense? Yeah? Is there a reason we chose powers of 2? No, there's absolutely no reason why we chose powers of 2. We could have chosen powers of 3, powers of whatever power you want, right? And there's actually no reason it has to be a power. We just need to choose a countably infinite set, right? And then we shift things down from a countably infinite set, all right? All right, so this is that's the idea, okay? So the hotel in this thing are the powers of 2, and we've shifted everything down twice, okay? So we claim, does it make sense now intuitively why this is a bijection, right? So we've just shifted everything down, everything here, and then we've kept everything the same. So we claim this map is a bijection. Okay? So if T is the set of 0, 1, where it's not a power of 2 or 0, so let's throw in 0 here. So that's like 2 to the minus infinity. But we have 0, we have 2 to the, I mean, that's not really important that it's just an extra point, right? 2 to the minus n here for n greater than or equal to 0, like this. Okay, so we've eliminated all the powers of 2. So then f restricted to t, okay, is a bijection. Okay, so it remains to show that that the map f restricted, let's say the map, let's write it like this. So we'll have 0, union, and then we'll have 1, 1/2, 1/4 here, like so. Mapping to this set, 1/2, 1/4, 1/8 is a bijection. So this is the induced map. Okay, so this is clear. Clear, since we have really, so 0 goes to 1/2. And let me just write them down again. 0, 1, 1/2, 1/4, 1/8, 1/16, and so on. And then, so here is 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and so on. Okay, and so this maps to here, right? So it is clearly a bijection. Okay, does that make sense? So this identity part's a bijection, and then this part's a bijection. Okay, so let me just make a remark. So as hinted, so this is more general. Than we presented it. So this proof really allows us to, so if we have a countably infinite subset, so if we have a countably infinite subset of a given set S, then this proof, then let's say then a modification of this proof will show that S union, I don't know, any finite number of points will have the same cardinality as S, right? So it's like we take the countably infinite subset of S, we shift everything down a little bit to make room for any new set of points that we want. Okay, that's the idea. Yeah?
Can that new set be countably infinite, or does it have to be finite?
So it depends on the, so I think it can be countably infinite, right? But I think the modification, so this proof, the proof that I gave right now only works for finitely many, right? But you can take, it is true that if you have an infinite set here, if you union it with a countably infinite set, then it's going to have the same cardinality. Yeah. All right. Okay. So let me give you a less direct approach. So another proof that these two sets are in bijection here. And so this is a proof by application of this theorem. So we will apply the so-called Cantor-Bernstein-Schroder theorem, which I'll state. And then I'm not going to prove this theorem. Okay, so let me state the theorem. So, oh, dang. Okay, I'm just like messing up chalk here. Okay, so theorem. And, okay, so it's, so if A and B are sets, so if A and B are sets, so then if we have the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, this implies that the cardinality of A and B are equal. So this is the Cantor-Bernstein-Schroder theorem. Okay? So note that we almost thought that this was baked into the definition of cardinalities, right? So let me tell you what this says in words, and then I'll explain why this isn't automatically clear. Okay? So, okay, so in words, what this says is that if we can find injections F from A to B and G from B to A, right, then these are not necessarily inverses to each other, right? But if we can find two injections, then there exists a bijection, a bijection H. All right, let me do it over here. So if you can find two injections, you get a bijection for free. That's what it says. Then there exists a bijection H from A to B. All right? So that they're equivalent. So all you need is you need to include one set in the other, like two inclusions, right? And then you'll get a bijection. Okay? So let me do an example. Okay, and so I'm going to try and do an example where this is not obvious. Okay, so we're going to let A be the unit disk. So A is equal to the unit disk in R2. And so it's equal to the set of xy, where x squared plus y squared is less than or equal to 1. Okay? And then we'll let B be the unit square. Okay? And this is the set, this is also a subset of R2. It's a set of xy, where the absolute value of x is less than or equal to 1, and the absolute value of y is less than or equal to 1. All right, so let me show you these drawings. Okay, so A so this is, say, radius 1. So this is the set A here. And then B, so x, y, okay? And then this is a square here, like this. This is B, and this also has length 1 here, size 1. Okay, and so this radius is 1, and then this is the half the side length. Okay, so so how can we produce? So to show that these two, so we claim that these two sets are bijective. These they're in bijection. The two sets are in bijection. Okay, so to show that there exists a bijection by the theorem, so this is like a cheap way of showing that two sets are in bijection. Yeah.
Never mind.
No, go.
Well, so with the unit disk, I'm just confused because couldn't you have a value that like would be less than or equal to 1? That would be like.
Yeah.
I guess.
Yeah,
I
like
guess
0,
it's
0 works. 0,
well,
0.
So I guess is there no like left bound of that circle? Because I guess it just
Left bound. This is -1 here.
Okay, so it's negative. Okay.
Yeah, and this is so this is a point, -1, 0. So it's bounded by the circle of radius 1, right? It's bounded by cosine theta, sine theta, right? Yeah.
So the definitions of bijection is like
So
injection and surjection.
yeah. A bijection is injection and surjection, or that there exists an inverse function, a left and right, which is a left and right inverse.
So like for the unit square, there is a point 1, 1, 1, right?
Yeah, 1, 1 is in the set. Yeah.
But 1, 1 do not include it in another side. Like 1, 1 because 1 square plus 1 square.
Yeah. It's so 1, 1 is it. So So for example, this thing sits inside of this thing, right? So we have, so A is a subset of B. B is not a subset of A, right? Okay, but the point here is all I need to do, so the idea, we claim that these two sets are in bijection, right? But let me say, but the bijection between them is not obvious. Is not obvious. Right? So there's a clear thing that A is a subset of B, but it's not a bijection because it's not surjective, right? And then maybe you could map B to A, right, by taking a smaller square inside of A, right? That would produce an injection from B to A, but it would also not be surjective. Does that make sense? Okay. But by the theorem, just because I get a map from A to B and B to A, which is injective, right? By the theorem, there exists a bijection. You don't get to write it down, right? I mean, there is a way to write it down, but we're not going to write it down, right? We just use this as a cheap way of producing bijections. Does that make sense? It gives us a test for determining when a bijection exists. Okay. So so let's note A, so the map f from A to B given by f of xy is equal to xy. So this is the inclusion map, E the inclusion map. So it acts as the identity here, right? It is an injection. Is an injection. Okay, and then the map here, so the map G from B to A, where, let's say, given by, let's say, G of xy is equal to x over 4, y over 4, is also an injection. And let me draw this picture. Okay, so here's B, like so. Okay, so this is so B is this set here. Okay, and then we have A. A is this circle here. And then what I've done is I've shrank the sides like so. Okay, and so the image here, this is G of B. Okay, and so this circle here, this this square maps to this square here, where now this side, this length here, is now a quarter. Okay, and I made it a quarter so it just fits inside. I guess I could have gone a little bit bigger, like 1 over square root of 2, right? Then it would be match up right there, right? But I just made it arbitrarily smaller. It's not so important what this function is. I made it small. Okay. So this map is also an injection. Okay. So by the theorem, there exists some bijection between A and B. Does that make sense? Okay. So in our particular application, so now we can do another claim. So another proof that these two things are in bijection. Okay, so So there is an injection here from 0, 1, let's call it F, 0, 1, this thing here, given by f of x is equal to x. So this is just the inclusion map. It's just the inclusion map. Okay? Yeah, so are you talking about why this is, it looks like a point, right? Yeah. So in Europe, and in Canada, they use this notation for intervals, and in the United States we use this. And so that actually prevents this from being confused with this. So my wife was talking about this yesterday. She's from Canada, and I was like, it's a common, this is why our interval notation is worse than this one, right? It's a good reason why that one should actually be used. But anyway, okay, and so there's another injection, the map G here. And so what I'm going to do is I'm just going to shrink this interval and stick it inside this thing here, given by let's say G of x is equal to 1/4 plus x over 2. So any line you have like that, you can check that it's going to be an injection, is an injection. And let me draw the picture. So what we did is we take, so here's 0, 1, like so. And then G, and what it'll do is here's the point 1/2, and so this is 1/4. So this is the open interval here, right? And this is 3/4, and it maps it here. So here's like, I don't know, if this is A, if A is this thing, then G of A is this subset here. Okay? So I've intentionally just shrunk it there. And so since there exist injections, and what do we call this? We call this one F and G. They're by the Cantor-Bernstein-Schroder theorem, there exists a bijection here between 0, 1 and the open interval and the closed interval, like so. All right. It's a very useful thing. Yeah.
So we can do like lots of other functions for these,
Yeah, you can do any function you want that's injective.
like gx equals to 0.1 times x.
So 0.1. So that would not work. So if you did, so you suggested to do g of x is equal to 0.1 times x. If you plugged in this one, x is equal to 0, right? Then you would land in 0, because g of 0 is 0 still. But if you just added a little something here, right, then that would work. That would be another example that would work. Yeah. Yeah. So that's something like that. So epsilon is a very small number.
And not greater than 0.9.
Yeah. I think any positive number here would work. So like any small positive number. So you could almost have this be a billionth, right? And that would work. Right? So 1/1,000,000,000. Okay. So that's what that's the Cantor-Bernstein-Schroder theorem. I'm not going to prove it because I don't think we have time. But let me talk a little bit about what I owe you now. Okay, and I'm going to try and do this stuff next class, and then after that we'll do the review on Friday. Well, where was I? Well, okay. Well, I think this is where I last stopped, right? Oh, I just finished there, so I'm supposed to erase this one. Okay. Okay, so what I owe you. Okay, so we have two definitions of infinity so far. Or we haven't talked about finite sets at all. Okay, so recall that we defined. So we defined a set to be infinite if it is in bijection with a proper subset of itself. Okay, so this was Dedekind's definition. Okay, so this is another one, but there's another definition we can give, right? So so we can give another definition. So we have really done nothing with finite sets. Okay, so so let's use this notation. Okay, so let me first define what a finite set is. A set is finite if and only if it is in bijection. It is in with n to the n for some n greater than or equal to 0. So some, let's say, natural number here. Oh, sorry, non-negative integer. Okay, so so recall that this thing here is the set 1, 2, all the way up to n. Okay, and we'll use the notation that this thing sub 0 is going to be the empty set. Okay, so an alternative definition of infinite, right, would be right. So a set S is infinite if it's not finite. Okay, so we need to show that these two notions coincide, that being infinite and being finite or being not finite are the same thing. Okay, so so we need to show that being infinite, not finite if and only if a set is in bijection with a proper subset of itself. Okay? And so, okay, so this is one thing that we need to do. And in order to show that finite sets don't have this property over here, we need to do something called the pigeonhole principle. Okay, and we have 10 minutes, right? Or it starts at yeah. Okay, so let me kind of give you the idea of the pigeonhole principle. Okay, so and then so let me give you kind of the idea of how these things work. So if you have an infinite set, if you can show that there's a countably infinite subset, right? To get a bijection with a proper subset of itself, is what you can do is you can take that countably infinite subset and shove it down one, right? We can do that trick that we did at the beginning, right? And what this will do is this will exclude, you take a countably infinite subset and then you kind of shift everything down one, and that'll be a proper subset of itself because of the starting guy that we shoved down, okay? But in order to do that, we need to show that sets with a proper subset of themselves, right, we have to show that 9 finite subsets have a countably infinite subset. Okay, so that's one thing that we would need to show. Okay, and then to show that finite sets are not in proper, or another way to show that, or a way to show that finite sets aren't in bijection with a proper subset of themselves is you have to talk about things like the pigeonhole principle. Okay, so let me just say what the pigeonhole principle is. Okay. Okay, so in applications of and around the pigeonhole principle. Okay, and so what's the pigeonhole principle say? Okay, so the pigeonhole principle shows that you can't have a bijection from, so the statement is, a bijection are strictly less than n. Okay? So here's the idea. Okay? So it's like if I have 20 pigeons in 10 holes, right? And I'm trying to shove the pigeons in the holes, right? Then this is impossible. There's going to be at least one hole that contains 2 pigeons. Okay? Or you can do nerds and lockers, right? You've got 10 lockers, 20 nerds that you're trying to put them in, right? You can't stuff them all in there, right? Okay. So this is the same thing, right? So it's like this is something that we actually need to prove rigorously. Okay. So okay. So I think I have to start stating some lemmas to get towards this. So I think I'm going to end the class here, right? And then we'll talk about how to put pigeons in holes in the next class.